Good day, everybody. I'd like to show you how to implement a CPM signal in MATLAB. That's really where you get to understand the algorithm fully. And we can read about it, but until you actually code it, you really don't know what's behind the process. So I'll start with this little illustration. I talked about this in class. The regular FSK, you can see that there are big jumps in phase discontinuity from one bit to another bit. These jumps create these spurious uh, spectral components. So the attempt is made to make the transition as smooth as possible. That's you go from regular FSK to a CPFSK. So then the example I asked you to implement was to essentially replicate this graph. And there's everything that CPM is about is embodied in this graph. At the top, you have the data. Then you have the phase trajectory, and on the bottom, you have the actual CPM signal. So if we do this, we really understand what's going on. The key to this is to implement the phase trajectory. So if you have a function in MATLAB that computes or expresses the phase trajectory the way it's shown, then you really have the CPM signal, and all you have to do is just plug that in. The expression we are really implementing is 114, where theta of t is in fact this curve here. So I'll show you how that's done. Once you have it, you just plug it into this, and then it's done. The other side is that what we are implementing is not just CPM, it's a CPFSK. And the reason it's CPFSK is because of this phase. The phase is linear in time. Anytime you have a linear phase in time, then you have an FSK signal. Why? Because the instantaneous frequency is the derivative of the phase. So if you take the derivative of the phase because of this plus minus sign, then the plus and minus slopes translates into jumps, as you can see. Now, depending on what h is, you either have a Sunday's FSK for h equal 1 or an MSK, minimum shift keying, for h equals 1/2. In our case, h is 1/2 because the extent of the phase deviation is pi over 2. See, a pi h is here is pi over 2 over the range, over the duration of the bit. All right, so let's bring in MATLAB here. I'll show you my code. So I'm going to drag this code here, and I've done it in segments so you can see how this is done. The first thing you want to do is you clear out the variables and the figures and whatnot. The second part is you set up your your variables that have really nothing to do with the algorithm. For example, you need to set your sampling rate. I picked it as 1,000. T equal 110. I'm basically plotting 10 bits. Each bit is 1 second. I'm picking the carrier frequency to be 1 hertz. So we have 1 cycle in 1 bit in 1 second, which is basically parallels what the example does. I'm defining my time array all the way from 0 to 10 seconds, and I'm backing off 1 over fs, which is 1 sample, to take care of the array length. Then I define my carrier. This is the reference signal. This is where 0 phase is defined. I'm using a sine. I could have used a cosine. I'm using a sine because the figure is using the sine. Then I'm plotting, and I'm putting some axis and grids and all that just to make it pretty, so you can see what's going on. So this is the carrier. So all these nice pretty grid lines were generated by that little piece of code. All right, so that's what we have. The next thing, which is the most important part, is the phase trajectory, right? the phase trajectory is either an up ramp or a down ramp. So I'm defining a new time array over 1 second. Then this creates the up ramp, essentially something the slope being pi over 2. All right, and then if I bring this back, then you have the up ramp and then the down ramp. The down ramp is the flip version of the up ramp. So I'm using B as a flip version of A, and then I'm simply stringing them along A, B, and then there are pi over 2 shifts to essentially replicate that. Now this particular piece of code is really tied to this specific data sequence, so it's really not a robust code. I have another code that actually runs on any data bits. So all you have to specify is your random data bits, and the phase trajectory is generated from that. So that's the superior code. But in any way, for this particular case, this is the phase trajectory exactly as you see in the graph. Notice I'm doing some little fancy things. The y-axis is properly labeled in radians, and so the rest is pretty straightforward. Now, the last part is to actually generate the CPM signal and superimpose it on the carrier so we can see the phase transitions. Now, for that, I did something a little fancy. It took me a better part of yesterday just to get that thing going. I'll show you what I'm talking about. This phase is given by this curve. I'll simply put it here. The number of array elements must be the same. So notice T here is this T. It runs over all 10 seconds. I'm taking the imaginary. I could have just written sine of the signal, so it doesn't matter. The rest are essentially a slow animation that I've implemented. So you can see what's going on here. The blue curve is the reference. The red curve is the CPM signal. The evidence that the phase is shifting is very obvious. Is look at the peak relative to the end of the bit interval. So here is right on it, then it shifts to the right, comes back to the left, shifts to the right, shifts further to the right, is coming back here, it back to where it was, and it's moving back, all right, and then it's moving back further. This is essentially a sign of and then all of a sudden is going the other way. So if I bring this in focus here, you can tell what is going on. So notice you start from 0 phase. The red and the blue are in the same phase. Now as you sweep the phase, notice this peak should have been really in the next bit interval, but it's moved to the left. So as the phase increases, the curve tightens. So the peaks are moving to the left. All right. So and then when you have the phase decreasing with the negative slope, the phase moves the other way. In fact, if you notice, the phase went up and then down, so it's back to 0, and that's exactly what happened in the second interval. See, the second interval at the very end, the red and the blue have the same phase. So everything is making sense. Everything is great and making sense. So this is just a very nice, beautiful illustration of CPM. I had never done this in this style and in this depth, and I myself learned a lot. All right, I hope you enjoyed it.